Welcome to this episode of the SCIEX Now Learning Hub, Introduction to LC-MS series. In this episode, we will talk about how ions are separated in time-of-flight mass analyzers. Like any mass spectrometer, a time-of-flight instrument consists of an ion source, a mass analyzer, and a detector. The type of mass analyzer, the flight tube, is what makes it a TOF instrument. In this video, we will see how a mass analyzer in time-of-flight instruments operates to separate the ions. Let's first have a high-level overview of the ion pathway in a SCIEX quadrupole time-of-flight mass spectrometer, along with a brief examination of the roles of its components. Ions are continuously generated from the LC flow and directed into the mass spectrometer's front end. They first enter the quadrupole mass filter, followed by the collision cell. You have the option to allow ions to pass through both components to detect intact analyte masses. Alternatively, you can select specific M/Z ratios in the quadrupole for subsequent fragmentation within the collision cell. The ions are then accelerated into the time-of-flight tube, where they are separated based on their M/Z ratio. They pass through two reflector regions that act as ion mirrors before their arrival is recorded by the detector. The resulting mass spectrum displays the distribution of ions along with their respective intensities. In this video, we will dive deeper into the operation and functional components of the mass analyzer. Before we go into the details of how a time-of-flight mass spectrometer separates ions, we will take a closer look at the flight tube, also referred to as field-free drift tube. It is located within the tower, which is visible from the outside. The term field-free indicates that there are no electrical fields or voltages interfering with the ions as they travel to the detector. Additionally, it is crucial for this part of the instrument to be maintained under vacuum conditions to prevent gas molecules from disturbing the ions on their journey. Let's first see how ions enter the mass analyzer in a time-of-flight instrument. They leave the quadrupole part in a continuous stream. An electrical pulse within the accelerator drives them as slices or ion bundles in an orthogonal direction into the flight tube. The ion bundles then subsequently enter the mass analyzer one after the other. This process occurs rapidly, allowing numerous ion bundles to be analyzed within a brief period. Such speed is essential to ensure that all ions present in the sample are detected, even if they arrive at the mass spectrometer within a narrow time window, because, for example, they have been separated by liquid chromatography. The acceleration region is composed of a pusher and a grid. We will now discuss the impact of the acceleration pulse. To illustrate the process in detail, we will consider three ions with different masses. The acceleration pulse defines the exact starting time point for these three ions, T0, which is necessary for accurate time-of-flight measurements. In addition, it is important to note that the pulse transfers the same kinetic energy to all three ions. Subsequently, they enter the field-free flight tube, which separates them, as we will see in a moment. So how are the different masses effectively separated? Remember, the three ions have different masses, but receive the same kinetic energy. As a result, the ions will have different velocities within the field-free drift tube. The lighter, that is the yellow ion, travels faster and gradually pulls ahead in the race to the detector. At the detector, the arrival of the ions is recorded. The lighter ion arrives first, followed by the middle-sized red ion, while the heavier blue ion takes the longest to reach the detector. The longer the flight tube, the better the separation of the ions. But since we know the exact starting moment of the ion's journey, the acceleration pulse, we can calculate precisely how long each ion took to reach the detector. This happens very quickly, typically within a few microseconds. This is an analog presentation of the principle of time of flight. Carefully observe the three balls of different weight. They receive the same kinetic energy, but gain different velocities, depending on their mass. In simple terms, the principle of mass analysis in a time-of-flight mass spectrometer is the exact measurement of the time that ions need to get from the accelerator to the detector. So far, we have only measured the flight time of ions, but we want to determine the mass, or rather the mass-to-charge ratio, of our analytes. By analyzing compounds of known masses and their respective charge states, their flight time can be converted into m/c ratios, a process called instrument calibration. Note that the intensity of the signals relate to the amount of analyte in the sample. TOF instruments enable simultaneous analysis across the entire mass range without theoretical limit. This example illustrates a real time-of-flight mass spectrum, showing the detection of multiple analytes with varying masses. In summary, during a time-of-flight measurement, ion bundles are generated in the accelerator, where the acceleration voltage gives all ions the same kinetic energy. The ions then travel through a field-free drift tube and their velocity, and thus the travel time to the detector varies based on their mass. Lighter ions reach the detector earlier than heavier ions. The flight times of known compounds are translated into m/c ratios, a process used to calibrate the instrument. Thank you for watching this episode. To view the full training course, including progress checks and a final quiz to earn a certificate, go to SCIEX.com. Log in today to take advantage of the highly rated training material offered in the SCIEX Now Learning Hub. You can use the links below.